In Chapter 7, we will be discussing nuclear fission. With it, we will talk about what it is, whether or not nuclear energy is safe and whether it's better than electric generated energy, and what happens to the waste of the nuclear fission. So what do you think about when you think about nuclear energy? Do you think about the Simpsons cooling tower? Do you think about Chernobyl? Do you think about bombs or toxic waste? Or do you simply think it's bad? It seems that most of us have an extremely bad opinion of nuclear energy. The electricity generated by nuclear power plants has increased in the last 35 years. However, it has maintained 20% of all energy resources. There is just over 100 nuclear power plants being used in the U.S. There have been no new nuclear power plants in the U.S. since 1978. In fact, the nine of them have actually shut down. The negative pictures you saw in the previous slide reflect Americans' point of view of nuclear power. This is largely the reason for no new power plants have been built. Throughout the world, there are only 440 nuclear power plants. This constitutes 15% of electricity that is being generated. Most of the United States power plants are over 30 years old and reaching their life expectancy. As of 2009, nuclear power generates 76% of France's electricity, while it only generates 20% of America's. Some countries like India are increasing their quantity of nuclear power plants. So a few of them are actually increasing rather than taking them down. Nuclear power plants are powered by fission. So what is fission and how does it produce energy? Fission is the splitting of a large nucleus into smaller ones with the release of energy. The energy that was holding these atoms together are then released. This is the result of Einstein's E equals mc squared equation. Einstein stated that when fission occurs, some of the mass that was in the original atom will be lost. This small amount of mass is turned into energy. If you have problems remembering what it actually is, think of the word fizz. When something fizzes, it bubbles up, while fission is when it bubbles out. E equals mc squared dates from the early years of the 20th century and is one of the many contributions of Albert Einstein. It summarizes the equivalence of energy and the mass, and the symbol C is 3 times 10 to the 8th meters per second. Essentially, it states that mass is turned into energy when atoms break apart in a nuclear reaction. So whatever mass this is that was lost is multiplied by this large number, and that's how much energy is made. Remember that an isotope is an element that has an atom. An element is an atom that has the same number of protons and electrons, but a different number of neutrons. As a result, the atomic number, which is the number on the bottom, will remain the same because the mass number on the number on top changes. The atomic number indicates which element it is on the periodic table. So if we looked at the periodic table and looked for number 92, it would say uranium. While the mass number states which isotope it is. When a large atom is bombarded by a neutron, so here's the neutron, The atom breaks into smaller atoms. So we have uranium at the beginning, and then it gets bombarded into barium and krypton. And momentarily absorbs this neutron, the uranium, and then immediately breaks into two smaller ones. If you count these numbers up, if you add those numbers up, you'll notice that 56 plus 36 is 92. So it's still there. It's just in smaller quantities. Fission occurs when the atoms break down. The atom is bombarded by a neutron, and it causes the chain reaction of the atoms breaking into two. Think of it like playing a game of pool. The first shot, the pool balls are grouped together in a triangle at one side of the table. This is the nucleus of the big atom. The cue ball represents the neutron that is bombarding it. When you hit the cue ball, some balls scatter off, some stay together, some move in the same direction, so they are all different in a different location but still together. This represents the breaking down of the large atom. Once again, when you're trying to remember what fission is, think of the word that it sounds like, fizz. The atoms are fizzing out and separating. So E equals mc squared, because c squared is equal to 9.0 times 10 to the 16th meters squared times per second squared. When mass is in kilograms, the energy is kilograms per meter squared per second squared, which is equivalent to a joule. These are the units that are equivalent. The large value of this c squared up here means it should be possible to obtain tremendous amount of energy from a very tiny amount of matter, whether in a power plant or in a weapon. When the amount of energy is calculated for just 1 kilogram, which is just over 2 pounds of uranium, it produces 33,000 tons of TNT. TNT, or trinitrotoluene, is used as a baseline to compare explosives. This is because they need to compare the new explosives to something that they were familiar with. So when we talk about the amount of explosion something has, it's referring to the amount of power in TNT. Rather than simply using nuclear fission for weapons of mass destruction, we are now using it as a controlled environment, in a controlled environment to produce energy. A nuclear reactor is a device in which nuclear chain reactions are initiated, controlled, and sustained at a steady rate, as opposed to a nuclear explosion where the chain reaction occurs in a split second and it's uncontrolled. So let's take a look at the basics of the nuclear reactor. The nuclear reaction is fueled by uranium dioxide, which is O2, uranium, and 2 oxygens. These are relatively the height of a quarter, so it's actually really small amount. These small pellets pack a lot of energy. These are then placed in fuel rods, the fuel rods of the nuclear reactors. So here's the fuel rods, and then they put a lot of the fuel rods together for the fuel assembly. These fuel rods are then placed inside water into the reactor vessel. Notice that there are control rods in between the fuel rods. These are to absorb the extra neutrons that scatter about. The control rods are composed primarily of an excellent neutron absorber, such as cadmium or boron, that can be positioned to absorb the neutrons as needed. These slow the reaction down. If they are completely lowered, they absorb so many of the neutrons that the reaction is not self-sustaining. With them up, the reaction is able to continue. The primary coolant inside the reactor vessel carries the heat away from the reaction and then heats up the water. Primary coolant right here, then heats up the water that's right next to it. It also moderates the heat of the reaction so that it doesn't get out of control. This then turns the water to steam, and from here the electricity is created very similar to that of the coal-generated electric system. The steam turns the turbine, so the steam comes out and it turns the turbine. Which then sends the energy to the generator that then converts the mechanical energy to electrical energy. The water then cools and condenses and returns to either a body of water or back to the steam generator. These cooling towers are what most people visualize when they think of nuclear reactors or nuclear power plants. The white cloud is simply extra steam that is given off. The reactors where the nuclear reaction is actually occurring is in the small cylinders with the white roofs in the foreground. All topics that we have been discussing, nuclear fission, nuclear fuel, uranium, etc., all rest on the understanding of radioactivity. Henry Becquerel was the first to discover radioactivity. He accidentally placed a mineral containing radioactive materials next to a photographic plate. This was back in 1896, before film was invented. So this was a really old photography plate, like one of these where you stick it in and then you pull it out and you develop it. So this is what the pictures typically look like. The next day he realized that the film seemed as though it was in the sunlight, even though it was protected by a black envelope. So there was a part of it that would not develop. Something had penetrated through the envelope, and this was the radioactive rays. Madame Curie, you may have heard her name before, decided to investigate this further and learned that the mineral contained uranium. She coined this term radioactivity, which means a spontaneous emission of radiation by certain elements. Further research discovered more specific radioactive particles, alpha, beta, and gamma. Try not to be confused by the term radiation. There are two different types of radiation, electromagnetic and nuclear. Electromagnetic radiation is referring to the waves of light, such as UV, visible, IR, microwave, etc. Nuclear radiation is referring to the radiation from a nucleus, alpha, beta, gamma. Alpha radiation contains 2 protons and 2 neutrons, just like a helium atom. This is why it is sometimes has a symbol of helium as the alpha particle. Notice the He there. The difference is that there are no electrons in the alpha particle. It is a small chunk of a nucleus that comes out of the nucleus. The beta particle is an electron that actually comes out of the nucleus. You may remember that an electron is extremely small weight, so the weight is so small that it's negligible. This is why the mass is 0. Notice right up here it has a -1 and a 0, because it still has a -1 charge, but it doesn't have a weight. But it does have a charge, which is why there's at the bottom it says -1. Finally, gamma. Gamma rays is simply energy. It has neither mass nor charge. It is a very, very high energy, very short wavelength. By an atom going through nuclear radiation, it is most likely changing the type of element it is. Remember, the atomic number indicates the element, so if this changes, the element changes. Notice that the element started with uranium. And then it was bombarded with neutron. Look at number 92 here. If we look at number 92 on the periodic table, it's uranium. 235 is the protons and the neutrons added together. Then it broke into smaller pieces. It broke into krypton and barium. If we look at the bottom numbers, these are the atomic numbers. So 36 and 56. If we add these two numbers together, it's up to 92, which brings us back to the uranium. So it's the same numbers, just in two different forms. If we look at number 56 on the periodic table, it's barium. That's how we got the Ba there. 36 on the periodic table is krypton. That's why we got the Kr there. That's where we get those from. Elements that are radioactive will continue to react and break down until it reaches an atom that is stable. All isotopes of all elements with atomic number 84 polonium are higher are radioactive. So if we look for element 84 on the periodic table, which is right here, anything greater than that is radioactive. This ends this part of chapter 7. In the next part, we're going to talk about some of the tragedies that occur with radioactivity.